So in case we have many degrees of freedom, like for example in a molecule, where we do have 3n minus 6 vibrational degrees of freedom if it's a non-linear molecule, or 3n minus 5 if it's a linear molecule, because of course you lose 1 degree of freedom, we will have to find a way to solve this kind of problem, because in this situation, of course, we have many oscillations. It's not a one-dimensional oscillator anymore. Now, in general, the Lagrangian of this system will contain cross terms of different degrees of freedom. So the Lagrangian will be in the form of, as you can see, there are all these kind of cross terms, and there are also these constants that do depend on both the coordinates. This makes life quite more complicated, because we can't consider the system as a set of distinguished coordinates anymore. That would make things much easier, but we have to consider the whole movement of the system at once. In fact, the equation would be, will be a sum where there will be all this kind of cross constants, of cross terms. So how can we make these things easier? We'll actually have to diagonalize this matrix in order to find a normal coordinate system. So we might imagine that x can be written as a complex constant multiplied with this complex exponential. That is actually the solution we found for one oscillator. Or better, x would be the real part of it, but now to write it shortly, we will simply substitute it in this way inside the equation. And actually, by substituting inside the equation, we can remove this time dependence. So I will directly, we'll have an expression in this form. So at this point, in order to have some non-trivial results to this system of equations, we have to impose the determinant to be 0. So this system of equations that requests our other system of equations to have non-trivial solutions will give us s omega squared results. It will have s omega squared roots, where s is the number of degrees of freedom of the system. Will be called characteristic frequencies or eigenfrequencies. And there will be the frequencies of our independent oscillators. So for each of our omega square, so for each of our characteristic vibrations, we can find a new vector that will be part of the new basis set, that will have the characteristic that if these are two new functions of my basic set, if I multiply them, they must be 0. In this way, I will have a normal coordinate set. I will probably normalize it in the end, so it will be orthonormal. And with this kind of coordinate set, I can have that q alpha double dot plus omega square q is equal to 0. And the Lagrangian will be in the form of, so as you see, what we really did is simply to diagonalize a matrix. We haven't done much more. We have simply looked for a basis set that was able to diagonalize the matrix, and so to remove any kind of cross terms. And in fact, now we can resolve the problem as many one-dimensional oscillators with this equation and with this omega alpha frequency. And that's actually what we see in spectroscopy, or in general in quantum chemistry, where we use this kind of normal vibrations and we consider the complete motion of our system as a linear combination of these normal vibrations. that it's actually the definition of using a basis set of vibrations. And this makes our life much easier, because as I said, you don't have to consider the whole system at once. You can resolve many single problems and then create a linear combination of them that will give us the movement or the behavior of the molecule in that certain moment. Of course, solving this kind of problems can be made easier if you have information about the symmetry of our molecule, but that's more advanced stuff. Of course, in case there is some kind of force, I can rewrite the equation exactly in the same way as we did in normal situations. Well, I will have some kind of force along this kind of vibration, so it will be exactly equivalent to what we have seen in the past. Nothing changes.